Hi, I'm Lakshmi from UC Berkeley, and I'll be talking about BGP security. This is joint work with Volker Roth, Scott Schenker, Jan Stoiker, and Randy Katz. So all of us know that BGP security is an important problem. Why? BGP as a protocol today blindly assumes whatever information you get from neighbors to be correct. Now, if a router starts propagating bogus announcements, which can potentially happen due to misconfigurations or malicious behavior, then you can have a lot of drastic effects. Let me explain some of them. So here is a simple topology where node M pretends to be malicious and propagates a bogus route saying it can reach CNN. And X believes, rather nodes C and D believe the advertisement and choose this route due to its local preference. And the route now goes through M, and M can just drop the packets. In that sense, it can render the network unreachable. A more sophisticated attack is it can impersonate with a CNN prime and serve different content. Or you can think about credit card server impersonation. Or even worse, you could just forward the packet on whatever routes you have, and you can just eavesdrop on the traffic. All these are serious attacks, and the basic problem is the router propagates bogus announcements. How do you deal with them? Now, there are several real-world examples. Misconfigurations have been documented a lot, especially the work by Ratul Mahajan in SICOM a couple of years ago. Some of the classic cases are AS7007 in April 1997 and 3561 in 2001. On the other hand, malicious behavior is actually a big threat. If you look through the NANOG mailing lists, and if you actually dig through them, some of the emails by Rob Thomas and other people show that several routers still have default passwords. Now, I don't know whether it's true today, but it does seem like a big threat. And Cisco issues several security advisories. I mean, a router is, for all practical purposes, like a computer. So if you can hack into a computer, you might as well hack into a router. And if we have one day where we have a large-scale worm attack on routers, what will we do? I consider that a doomsday scenario. Now, there are two basic types of invalid routes in BGP. Now, whenever we say a router propagates invalid routes, we talk about invalid routes in the control plane, where somebody propagates a route which is non-existent and tries to divert traffic. But on the other hand, a recent work by Morley Mao showed that several routes in the data plane, that is the actual path taken by the route in the data plane, does not match the route in the control plane. I mean, that can happen due to several legitimate reasons. But the bottom line is, if we verify the routes in the control plane, it may be insufficient. Just because the advertisements in the control plane are correct, it does not imply that the data plane route is working. So what is the bottom line out of this argument? We need two verification techniques. One, to verify correctness in the control plane, and number two, to verify correctness in the data plane. And that is exactly what we do. We develop two techniques, one which we call as listen, and the other one which we call as whisper, motivated by Chinese games actually. There's this old Chinese game called Listen and Whisper, so we got the name from that. And Whisper basically does control plane verification, and Listen basically does data plane verification. And the basic problem we try to address is what best security can be provided to BGP without using a public key infrastructure. Now, why do I say that? There have been several very good proposals for improving BGP security, secure BGP, secure origin BGP, and they have faced several deployment problems. PKI is not just about performance issues and so on. There might be even political issues in deploying a PKI. For example, whoever owns the root of the PKI has tremendous power. And situations like a war or anything, you can misuse the PKI route. You never know. So why should somebody in other places give the PKI route so much power? So whether a PKI-based solution is deployable or not deployable, I don't want to argue here. But the bottom line is we might also want to do research on what are solutions without using a PKI. Just a brief comparison to related work. There are several PKI solutions which offer very good security, but my premise is they are hard to deploy. And primarily they look at control plane verification, as I briefly said a couple of minutes ago. And there are some ad hoc solutions which try to use centralized databases. And these databases are incomplete, and they offer very little security properties. There's some nice work by Feimster, Jennifer Rexford on configuration checking tools and some other folks as well. And this is very useful. This is very useful for detecting misconfigurations. However, it primarily applies to control plane misconfigurations and may not apply to data plane misconfigurations. On the other hand, there's another work by Morley Mao and Jennifer Rexford. Again, Jennifer has done a lot of work in this area, which is useful for data plane probing. And so one could think of a combination of these two to deal with misconfigurations, but they do not deal with malicious behavior. Now, our work tries to provide the following guarantees. In the control plane, we provide the ability to trigger an alarm. That is, whenever somebody tries to propagate an invalid route, we try to trigger an alarm saying something bad is going wrong. So whenever a compromised router propagates a single invalid route, some network operator will get a signal saying something bad is going wrong. And the problem over here, as I will get in a little second, is we might not always be able to pinpoint the source of the problem. But when somebody tries to attack the infrastructure by propagating several invalid routes, then we can contain the person. By contain, I mean we can contain the damage that single router can cause. On the other hand, the listen technique for the data plane can notify the existence of data plane problems without sending any additional packets. It is completely based on passive probing. So now I'll get into the control plane mechanism in a little bit more detail. So the primary difference between a PKI-based approach and our approach is the distinction between authentication and weak authentication. In our case, we define the notion of a route consistency test, where each route is associated with some hash value. We call it HP in this case. And a single route advertisement by itself does not have any meaning. But when you take two such route advertisements to the same destination, as in same destination AS or destination prefix, then you can compare the signatures of these two and see whether they are consistent with each other. Now, what does consistency mean? Now, if both the routes are genuine, that is, if the AS path specified in the AS is actually the set of ASs it traversed, nothing has been changed, then it's a genuine route. If both the routes are genuine, then the route consistency test should tell you that they're consistent. If one is genuine, one is spurious, it should always tell you that they're inconsistent. But if you have both of them to be spurious, that is at least one malicious node or misconfigured node in both the paths, then you really can't say what the test is. Now, in a while, I'll tell you how to construct this test in the next slide, actually. But before that, what does route consistency give you? What does this abstract concept give you? It gives you the ability to trigger an alarm. Assume that everybody in this world is good, and there's one bad person who propagates invalid routes. Then, if he's trying to attack a particular destination network, and he's not on the path to the destination network and tries to get into the path, then there are two advertisements. One from the good node, and two from the attacker. So if you consider Y to be the attacker, A, B, C, D will be good. But the route propagated by Y might be bad. So you'll always have two routes to compare at some AS. In which case, the node D will be able to trigger an alarm saying something is going wrong. So the basic concept of route consistency gives you the ability to trigger an alarm. Now, how do you exactly do it? Now, this slide has some math in it, but let me give you the abstract concept. There's a node A which starts with a seed, which I have constructed based on RSA. And what every intermediary AS, every node in this figure is an AS, like B is an AS. So consider B to be a single router in an AS. What B does is it gets a signature S, which is of the form G power Z the whole power A mod N, and just exponentiates it. That is, if I get a signature S, it computes S power B mod N. Now what is N? N is a product of two primes. Given N, RSA guarantees that you cannot factor N. And what does it mean for us? When somebody exponentiates a signature with their AS number and appends the signature in the BGP route advertisement, nobody else can remove it. So I repeat, if I add an AS number to the AS path and I append the signature, you cannot remove it because you cannot compute discrete logarithm. And that is the basis of this construction. However, if you consider the two signatures, S1 and S2, one is G power Z the whole power A, B, C, and the other one is G power Z the whole power A times X times Y. What is different? In one case, X and Y are there, and in the other case, B and C are there. So you take these two signatures and exponentiate with whatever is missing. That is, you take S1 and you exponentiate with X and Y. And you take S2 and you exponentiate with B and C. And you basically get you need these two to be equal for them to be actually consistent. So if anybody tries to manipulate the AS path, these two will not be equal. So if one of the routes is genuine, the other one is spurious, you'll always notice an inconsistency because you cannot also compute the signature. You don't know G power Z the whole power for a given path. So I have 5 more minutes. So what is this useful for? Consider a node M that is propagating 3 bogus routes, one to A, one to B, and one to C. In this case, you get 3 pairs of consistency testing, DA, MA, EB, MB, and FC, And you'll notice that all these 3 pairs through 3 different destinations are inconsistent. So you'll notice 3 inconsistent route advertisements from M. One interesting aspect of the previous construction is if 2 AS paths are inconsistent with each other, then at least one is spurious and the liar is always present in one of the AS paths. So in this case, M will always be present in one of the AS paths. This is a very simple way of ensuring that. So you can assign penalty values to each AS. And in this case, penalty of M becomes 3, just the number of route advertisements to different destinations. And you just choose the route with the least penalty. And that way you will avoid M. So what does it look like in the internet? Assume that all the tier 1s deploy this defense. Then the remaining portion of the network consists of little clouds. If there is one attacker in one of those clouds, you can show that that attacker in the worst case, if that is the only attacker, it's an isolated adversary case. This argument does not work for colluding adversaries case. If that is the only attacker, then he can only affect people in that cloud. And what the next graph tries to show is that the portion of that region is only 1% of the internet topology. Now, we can get into the details of the graph later. What I've shown is the fraction of nodes vulnerable to the attack, which is the size of that cloud, and I've shown the cumulative distribution. And you can read off the median value to be 1%. So the containment region is limited to 1% of the topology. Now, this is just a simple slide which shows that we have implemented the whole stuff in a router in a Zebra implementation, and it actually works very well. So all our operations, cryptographic operations, can be we can process it at a rate of 100,000 advertisements per minute. So you can essentially offload it to a CPU. While the maximum load observed today is 9,300 advertisements per minute as per Sprint-Mon's website. So we can process 10 times the current rate. So it's no big deal. Now let me briefly summarize the data plane verification. The basic approach of the data plane verification is to listen to TCP connections. If I observe a SYN packet followed by a data packet at a router for one flow for one prefix, it means that the route works. Why? If the SYN is followed by a data, it means that the SYN has been acknowledged. So the route is working. You have received a response from the destination. Now, there are two possible scenarios of false positives or false negatives. One, a port scanner sends only SYN packets. So do you assume that the route does not work based on that? Or the false positive scenario is an adversary sends SYN and data packets without receiving ACKs. Now, we have developed defenses for both these techniques. Now, I won't get into the details. And we've deployed it in our local area network for the last 4 or 5 months, and we have observed several routing problems. So, in summary, there are 3 basic types of problems: misconfigurations, isolated adversaries, and colluding adversaries. Now, the set of defenses I've briefly explained do not work very well for colluding adversaries. But I believe it's a good first line of defense, where you don't use a PKI and you get good protection against isolated adversaries. And whenever somebody propagates a bogus announcement, we can trigger an alarm, and we can trigger data plane inconsistencies, and we can also contain a single node. But it does not work well when you have a large-scale worm attack or you have colluding adversaries. Thank you.
I think we have time for one question if anybody has one. And identify yourself.
David Barak, AT&T. Given the number of routes in the global table which are currently advertised by inconsistent autonomous systems, how would Whisper deal with that?
Sorry, can you repeat your question?
I'm sorry. There are a large number of routes in the global table which are inconsistent and are normal. Because people announce them from a variety of different autonomous systems. So wouldn't those be tagged as inconsistent via Whisper also?
For example, if you do path stripping, which is a common thing today, it will be triggered as an inconsistency.
No, I'm talking about routes which are just in the unicast internet world that are completely inconsistent.
So 2 different origin ASs, if the origin AS actually advertises them and generates the initial signature, even if you have a virtual AS number which is not prepended in the path, and if it is a multi-home customer, it will not trigger an alarm. Because if you have a path ABCD and if you have a path AXYZ, say, and both originate at some point M prime, and M prime is not present in the path, but if M prime generates the initial signature and forwards it to both its providers, D and Z, and if M prime is the only difference, then it will not trigger an alarm. But if you have going through multiple or the providers themselves generating Whisper signatures, then it will definitely trigger an alarm. Does that answer your question?
I'm not completely sure.
We can keep it offline.
Okay.